Let's start. We are very happy again today to have Aya Ismail to talk about interpretability in deep learning. Aya is a PhD student in University of Maryland, and she is an expert in this area. So we are very happy to have her tell us about this problem and recent advances in this topic. Without further ado, Aya, screen is yours.
Thank you, Sahil. Okay, so we'll be talking today about interpretability in deep learning. So basically what we have is we have an input, and then we have a black box model, and then we get an output. And by model interpretability, what I mean is that I want to understand why a model made a certain prediction. So why do we care about interpretability, and why can't we just trust the model and use the decision that it makes without understanding why it made that particular decision? Well, the main reason is because in real-world applications, accuracy is simply not enough. So let's take a look at some examples where we would need interpretability. So, for example, if we have a model that is used in industry, and then we need to identify if it has undesirable behavior. So basically, we want to make sure that it's making the correct decisions for the correct reasons. Like, for example, an AI was used to see if a person should get bail or not, and then after using it, people notice that it's giving the bail decision based on color, and it was, so basically if somebody was black, he was more likely not to receive bail than other people. So we may need to make sure that it's making the correct decisions, and that is for the correct reason. Another case is that what if we want to improve our model performance? If we know why the model is making a prediction, then we can just simply go and try to fix it and get models with better performance. One other reason we might need this is for scientific discovery. So basically, neural architectures take all of these inputs and try to understand patterns and underlying distributions that we as humans might not know ourselves, and in some cases we would really want to know this. Like, for example, if a neural network is used to classify human brain activity, we would want to know, so what areas in the brain are responsible for what functions. This would be very useful in many scientific applications. And the last thing, well, basically sometimes applications are too critical to just say that, well, we made this prediction and that's it. For example, medical applications, you kind of have to explain to the end user why you made this application, and you can just say that, well, it's because we have this black box model and it said so. Okay, now that I hopefully convinced you that model interpretability is really important, let's dive into a little bit about interpretability methods. So first we can have baked-in model interpretability. What do I mean by that? That we have this model and we train it to explain itself. So when it has it's given an input, it's able to provide an explanation of why it made a decision for that input. Another interpretability option is feature level interpretability, which is basically we have a group of features and we want to know the contribution of every feature in the final prediction. There's also instance-based explanations, where if we have a test example and it made a prediction, we want to know which training example were responsible for that prediction. And finally, there's this global decision rules, where we want to understand the global reason why the model is making a certain prediction. So kind of high-level understanding of the model itself. So basically what we're going to be focusing on is feature-level interpretability for this lecture. Okay, so again, for feature level interpretability, we're going to define it as that if we have a trained model, and we have an interpretability method. What it does is it assigns an importance score for every feature that correlates to the importance of that feature for a given prediction. And this is shown through Saliency Map, which is basically a feature score map. So there's different types, two main types of saliency maps. There's perturbation-based saliency maps, which is basically means that, well, I take my input and I pass it through my model and I get an output, and then I perturb an input, one of the features. I perturb one of the features and I pass it, the new input to the model, and I get another output. And basically, the contribution of that feature is the difference, the change in the output of the model. And there's different ways we can do that. So, for example, there's this leave one out method where it just removes the feature altogether, and see how the model is affected. There's feature oscillation, where you kind of perturb the feature a little bit and see how that affects the model. And there's other methods as well. So another class of saliency methods are gradient-based saliency methods, and these are kind of more popular. So there's a huge list of gradient-based saliency method, and this is not like all of the methods that we have. And every conference there is a lot more coming out. So basically, let's take a look at gradient-based methods a little bit. So the first thing we have is input gradient, which is basically the simplest thing we can get. So we have this input, we pass it through the model, and then we have a probability for every class. So we take the class with the highest probability, and then we calculate the partial derivative of the output with respect to the class with the given input. And what this partial derivative is showing me, it shows me which features do we need to change the least to get the change, to get the most change in that particular class. And we end up with the saliency map, which basically what it does is that it highlights the important features in that needed for that model. Okay, so what does the partial derivative mean, and why does it make sense, and how is it actually doing this? Well, if we kind of plot it, basically what it means is that the derivative is basically this tiny change in the feature input. So here, if this is the input, then the derivative is basically the smallest change, a really, really tiny change, and that's why it kind of represents the output when we change the input. Okay, so this is the most basic method that people can use when it comes to gradient-based methods, and it has some limitations. So one main limitation is that it's very sensitive to small perturbations. So for example, here, if we just move this input a little bit in either spaces, we get a very different gradient. Another problem is that we can have this saturated output that lead to intuitive gradients. So if we look at this example here, we have y equal x1 plus x2 if x1 plus x2 is smaller than 1, and 1 otherwise. So let's say that we have x1 and x2 both are equal to 1, and we want to calculate the gradient, and then we get this gradient is 0. So what does that mean? It means that both features aren't important, or it's really not intuitive and doesn't help us understand what's happening. We also can have this discontinuous gradient problem, where we have an input, and then where we have, for example, here y equal the maximum of 0 and x minus 10, and then when you plot the gradient, it's basically the step function where it's 0 and then it's 1. First, it has two problems. One is that the sudden jump. The other one is that the gradient doesn't show anything about the value of how x changes at all. Okay, So how do we address this? So people started to say, well, you can't really rely on a single gradient. Let's look into multiple gradients to calculate it. So let's not look at just a single gradient. And the first method that we're going to discuss is called smooth graph, and that's basically the idea behind it. So what does smooth graph do? Well, smooth graph takes the input, and what it does is that it adds a Gaussian noise to the input, and then it calculates the gradients of all of these new inputs, and then it averages them. And then the new gradient is the average of all these gradients. And then basically what it means that by doing this, we don't have this like really sensitivity or locality of the gradient anymore, because we took a group of gradients. And you can see here in the example they provided in their paper, where if you have this gradient saliency map, which is not doesn't show the tempo at all, but if you do the smooth grad where you have multiple gradients and average them, you you're able to find a clear tempo and kind of understand which features were important actually. Okay, this is one method. Another method is called integrated gradients. So basically what this method is saying, well, we're not going to look at just we're not going to just look at random inputs. We're going to take a reference point and see, well, how x changes from one point from like the first point to the last one, and then see how the gradients also change. So basically it's just looking at the integral where if x change from x to x dash, and looking at how x changed from x dash and multiplying by how the gradient changes from x to x dash. So since we don't actually calculate the integral, what we do is that we calculate these gradients at different step points, and then we just average them and multiply that by the change in the gradient itself. And then when we look back into the problem that we looked at previously, where we have these where we have this step gradient function and it's not indicative with the input, if we do this integrated gradient, well, we still have this step problem. But here it's a little bit better in that it's it kind of shows how the input changes. So basically here it's going to equal 10, and the gradient is going to be equal to 10 at this point, and then increase basically with the increase of the inputs. If we assume that this is like our reference is basically 0, or whatever the reference is, it's going to increase. But if we have a constant reference across the samples. Okay, another method that came out most recently is called deep lift. And what deep lift does, it has this really cool idea that says, well, actually, we don't really care about y as x changes at that particular point. What we care about is the slope. So basically what that means is that we care about the slope of how y changes as x changes. So let's take a look at the example and see what that means. So basically, let's say that we have this point here, and this is the point x. This is the first point. The green point is the point that we're actually looking at. And if we look at this point here, x has -1 and y is a value, so it just has 0. And if we calculate the gradient is basically 0. Instead of looking at the gradient and saying that the gradient is 0, well, no, what we're going to do is going to take this reference point, our baseline, and then we're going to see, well, if we change x from here to here, so x is going to change from -2 to 2, how much is y going to change? So in this case, y is going to change from 0 to 2. So there's a change in, so x is going to change by -4, and y is going to change by -2, and so that gives us a slope of 0.5. We're going to multiply that by the change in x itself, and then that's kind of going to be our feature importance. So it's basically like how the gradient changes from a reference point when the input changes from a reference point. And this makes more sense because in that cases, we kind of understand what happens in the model with relative to this reference. One problem with deep lift in general is that you kind of need to have or know a good reference point that you can calculate your gradient from. There's other methods that are also popular gradient-based methods like SHAP, which is basically use this game theory approach to kind of assign feature importance. There's this deep SHAP, which combines deep lift and SHAP values, and there's other methods as well. And these are not also the only methods that we have. There's many more. So one thing to note that all of the methods that I mentioned are used for a first order interpretation. So what I mean by that is that basically we're getting the first order gradient. So there's some of the recent work that was done by Sahil, a student in our lab as well, that he started to look at second order interpretation. And basically what he showed in his paper was that if you have like very small confidence, then second order interpretation are better than first order interpretation. But if you make an output with high confidence, then basically the two interpretations are kind of the same. There's not a difference between them. And on how he made the second order approximation, more details about that is available in his Ismail paper. So before I go on, up till now, does anybody have any questions? Would smooth drag be equivalent to applying a blur operation, then taking the input of grad? Yeah, yes. So you can apply they add Gaussian noise, so it's kind of like blurring, but you don't do it once. You do it multiple times. What if the confidence of the model is not correct? I mean, the confidence of the model is an approximation. So the idea is that well, if you have high confidence, then you probably second order interpretations are kind of give you better results. So why is this true? Why is the second order interpretation? What's the second order interpretation with the confidence? I'm not sure exactly why this is the case. They had a really long proof in their paper. So if you're interested in that particular second order interpretation, you can check out their paper. Other questions about feature level interpretability in general? Okay. Okay, so now that we kind of looked at gradient-based interpretation, let's kind of see if it has limitations. So one huge advantage is that it's really cheap, right? You just calculate you make a single pass on the model, and then you just make one backward pass, and then you have the explanation. So it's really cheap. So what are the limitations? Well, it makes this huge assumption that the model must be able to faithfully calculate the gradient of the input with respect to the output. So okay, that makes sense. So basically the model should be able to calculate the gradient of the input with respect to the output. Why is that really a problem? Well, let's look back back to what we said last lecture. So last lecture, what we went over is recurrent neural networks. And then we said, well, recurrent neural networks are bad because they have this vanishing and exploding gradients. And then we talked a little bit about LSTMs and said how they fix the vanishing and exploding gradients. So let's see what we get if we test LSTMs on these gradient-based methods. So let's say that I give you this input, and this is a time series, and here I have time, and then I have features, and these red boxes are my important features, and the rest is basically Gaussian noise. So this is like, if we assume that this is a positive example, a negative example would have like these boxes would be dark blue for it, and then the other is also Gaussian noise. So what we know is that the important features are in these early time steps, and the rest is basically noise. Okay, so we have an LSTM classifier, and after that we train it and we get an output, and we have really high accuracy. And then we take this output, we pass it through a gradient-based method. And since we know that the LSTM has high accuracy, then we know that it's usually using the informative features, because if it wasn't, it wouldn't be able to give us the correct output. Well, what happens is that if we pass it to any gradient-based method, anyone we mentioned, we end up with a saliency method, a map that looks like this. So what is this exactly showing us? It's showing that there's like small importance on the last few time steps, and it doesn't put any importance on anything in the beginning. So why is there a vanishing saliency? So we kind of noticed this behavior in a paper we published last year in NeurIPS, and let's look into why we have this vanishing saliency problem in general. Okay, so what we were talking about last time is basically the derivative of the weight with respect to the error. And that's what we need for training and backpropagation to update the weights. But for saliency, we're looking at the derivative of the input with respect to the output. And that's like kind of what we've been saying in the beginning. So basically, let's say that, okay, how is this different? If we have our LSTM and we have our equation that we showed last lecture, and then we want to calculate the partial derivative of the output, which is at the last time step with respect to the input. So, and we write it out, it's going to give us this huge equation, which depends on the d of, so the partial derivative of every LSTM cell with respect to the first one, up till we get to the input that we're interested in. And last lecture, we showed that this partial derivative of h of t with respect to h of t minus 1 can be approximated to this equation, where it's just basically the output multiplied by some sort, depends on the output, the cell state, and the forget gate. So what that means is that the information that's preserved it depends on just the forget gate. So if we look at the earlier time steps, as we go in earlier in time, this contribution is going to decrease and decrease and decrease, and eventually it's going to vanish completely. And if we set the forget gate to 0 at any point, what we end up having is that there is no direct gradient path from the output to the input. Okay, and that's why we saw this vanishing saliency problem that we mentioned. So how did we fix this? Well, one thing that we could do is that we kind of combined the two ideas that we talked about, which is, well, we have a recurrent network, but instead of giving it the input x t at every single recurrent cell, what we're going to give it is all of the previous time step up till this xt, and we're going to multiply that by an attention, and then we're going to end up with this matrix, which is a fixed size embedding that's going to be the input to our cell instead of x of t. So what does that look like? So basically we take for every cell we get this all of the inputs up to that particular cell, and then we do this attention, which is multi-layer perceptron attention, and we get the weight for every single input. And then now we have this matrix M, which is we multiply that input with the weights, and then M is fixed size. And then we change we change the gates. Instead of having like the weights multiplied by the input x of t, we're going to multiply it by m of t. And now at every single time step where there's a direct gradient path from the output to the input, so we kind of can look at which inputs it's actually using. So if we test this again, what do we get? Okay, so we used to have this vanishing saliency map, but when we do that, when we use this new architecture which we called LSTM plus input cell attention, because we have self attention on the cell level, we end up with this new saliency map where it kind of highlights the important features at the beginning, and it doesn't at the end. It doesn't give us a perfect saliency map, but at least it doesn't have this vanishing saliency effect. So yeah, so it kind of it reduced this vanishing saliency. So that's the first limitation for gradient-based interpretability. So any questions up till now? I think somebody had a question. Oh yes, so there's a question says that is there any concept of conditional importance that is inspecting how important features are when they exist together instead of looking into independent features alone? Yes, so actually that paper that Sahil did and published that was looking into second order interpretation was also looking into how we can, instead of looking at single features, we can kind of look at a group of features that are related and see how changing these groups, the related groups, affect the output. And that kind of makes sense. That kind of makes sense in the sense that, for example, let's say that we have this sentiment analysis, and I said the movie is not good. So basically, not and good are both important for me to say it's negative. So that's kind of the idea of grouping. So yeah, there's some work about that, and that's one of the things that he looked into. Was there an MFT for every time step? Yes. So basically, yes. So there's every time step has different x of t. So in that case, we have different MFTs for every time step. Does this issue of faithful gradient calculation exist in only RNNs and LSTMs? Yeah, so that's kind of what, so if we try this with a convolution neural network, it works. We looked into this in transformers, it works, but we found this issue with any recurrent network in general, GRUs, LSTMs, and other gated networks. If there's some other architecture that is not under these categories, I did not test myself, but this vanishing saliency is kind of basically observation is new. It was only like we only published last year, so apart from RNNs, I'm not aware of any other architecture that has this problem. So what do you think is a perfect saliency map looks like in LSTM? Since you said that you didn't find a perfect saliency map. Well, a perfect saliency map, I would want to focus on the important features, right? So here there is these kind of noisy inputs where there's these lines that don't really make any sense, but it kind of highlights the importance. So a perfect saliency map, what we would like is that it wanted to focus on important features and only important features. Is this a kind of self-attention? Yes. So this is basically self-attention on the input level in every single time step. Okay. Since this is all the questions, I'll be moving on. Okay, so another problem is that interpretation of neural networks is fragile. So what do I mean by that? Let's say that we're giving this input here, and then we pass it through a classifier, and then we get an output, and that output is correct, right? And then we give it to a saliency, gradients-based saliency method, and then we get these saliency maps, which kind of makes sense because when we look at it, well, we see that it's kind of highlighting the 7 and the 5 and the 6. So it's understand which features are important. So great. Okay, now let's do what we did in the adversarial lectures that Suhail discussed earlier in the term. We're going to take this input and make like small perturbations that for us humans should not affect the output of the classifier. So we took this and we have these very small perturbations, and then we sent it to the classifier, and the classifier gave us the correct output. So we don't have an adversarial example, and we're happy. So since we're able to classify it correctly, then we would expect that we get good saliency maps, right? Well, no. What we end up with is these really blurry saliency maps that made no sense whatsoever. So, okay, so why is this happening? And why do we get like these really good, why do we get this really bad saliency map, although we didn't have an adversarial example and we were able to correctly classify? And more importantly, is how can we fix it? So by fragile here, I mean that if you have like very small changes in the input, you end up having huge changes in the interpretations with that resultant interpretation that makes no sense whatsoever. Okay, so when we were looking at adversarial examples and adversarial training, what we said that, well, if we have this adversarial example, it's what we're going to do is that we are going to do this adversarial training for classification. So how we're going to do that is that we're going to attack the inputs and then use this attacked inputs and train the classifier with the attacked inputs, and then that's how we kind of defend against that attack. So okay, what if we do exactly the same here? So this work was done by Alex Levine, which also is a student in our lab. And what he noticed is that, well, if we do adversarial training for classification for this particular task, we still have really bad interpretations, and also the interpretations without the perturbed interpretation becomes also worse. So they kind of started to think about, well, maybe for adversarial, when we have an adversarial example that causes the classification to change, we did adversarial training for classification. What if we have adversarial, so if we have an example that causes the interpretation to change, maybe it makes sense to do adversarial training for interpretation itself. That's what he looked into in his paper, and basically what he found is that, well, you can dramatically improve if you do this adversarial training for interpretation. You can dramatically improve that compared to what we had previously, and also the regular interpretation are much better than the original one. So you get this new saliency map for the perturbed inputs that looks pretty well, and then you get better, even better for the regular inputs. So exactly how he was doing this adversarial training for interpretation, well, basically he changed the loss function that so the loss function here is different from that was explained in the adversarial training for classification, and you can check his paper for more detail about the adversarial training for interpretation. Okay, another limitation is that we kind of need a white box access to the model, right? We kind of need to be able to calculate the gradient of the model. We can't be given a black box model and ask and use this gradient-based methods. And another thing that we said that we always calculate the output with respect to a class. And now, what if we don't have classification tasks? It's more tricky to use these gradient-based approaches when we are looking at problems that are not classification problems. So these are the some of the limitations of gradient-based interpretability methods. So before I move on, what is do you have any questions? So what is the objective for adversarial training? So the objective itself is you can find it in the paper, but basically the idea is that we want to the loss itself is going to have like this, it's going to have basically what it does is that it has like this term that is the interpretations, the interpretation itself in the loss, and that's how kind of they train. But the exact loss function and details on how they do the training is available in that particular paper. Other questions? Okay. So if I said that getting good accuracy may be hard, then definitely getting good interpretation is way harder, right? So what about evaluation of model accuracy? Well, that's really simple. You have this one task, and then you get these two models. You train them on the same task. You get to the outputs of the models, and then you have these ground truth. You compare the output with the ground truth, and then you get the accuracy of the first model, accuracy of the second model. And what you say is, well, if the first one has better accuracy, then the first one is better. If the second one has better accuracy, then the second one is better. And if all you care about is accuracy, then you're done. And this is really easy and simple and clean. Okay, so what about evaluation of interpretation? So what do we do? Let's try to do the same thing. Well, we have this black box neural networks, and then we have the saliency method, the first saliency method. We have a second saliency method, and the first one gives me an explanation, and the second one gives me a completely different explanation. Okay, and then what? What do we do next? So basically, if we knew what the correct explanation is and what the model exactly was doing, we wouldn't need to have interpretability methods at all. So we end up with this egg and the chicken problem where we don't know what the model does, so how do we evaluate these methods that tell us what the model does? So is it like impossible? So is it this is a hopeless case and we can't really go forward, moving on? Well, not quite. People try to kind of make smart kind of smart like methods to kind of evaluate these interpretations. Okay, so the first simple thing is human-based evaluation, where I'm going to take a human and I'm going to give him these outputs of different methods, and I'm going to ask him to tell me which method gave him the most indicative or the saliency map that made most sense to him. Well, this has two problems. First, we assume that the human can understand this explanation. And that's the case in really simple tasks, like, for example, sentiment analysis. So if I give you a sentence that I love the movie, and I and one method tells me that for a positive sentiment, love was the most important feature, and another method tells me that I was the most important feature. Well, that's simple. I'll just tell you the first one that says love is most important is actually the correct one, because that makes sense. But what if I give you a saliency map of the human brain, and I tell you, well, this method tells you that this area of the brain is more active when you do that particular task, but this method tells you this area of the brain. Well, we don't really know what the truth is, so even as humans, we won't be able to evaluate this. And another problem with this is that basically we're assuming that humans and the model are making the decisions for the same reason. And this is not always the case. Sometimes the model understands that the humans don't know, and sometimes the model is doing stuff for the wrong reasons that we mentioned earlier in the lecture. Okay, another way we can look into this is looking at the accuracy drop after removing the salient features. So what does that mean? Well, it means that, well, we have this trained model that we give an input and we get an output and we get an accuracy. And then we pass the output to a saliency map, we get the saliency method, we get this map. We take this map and we take the input, and basically what we do is that we mask the features that are called are the most salient or the most important. And then we take this masked input, we pass it through the trained model, and then we get this accuracy. And what we're saying is that, well, if we have this huge accuracy drop, then basically what that means um, is that, well, the model, the saliency method was able to identify important features, but if we get a smaller accuracy drop, then maybe it's doing a good job in identifying important features. Well, this makes sense, but the problem with that is that there's this recent work that was done by Google Brain last year in Europe that was saying, well, actually, you know what? The accuracy drop is not, it might not be a result of masking or removing important features. It might but be the result of masking themselves. So if you mask anything, you're going to get an accuracy drop because you change the input distribution significantly. And if you want to use this method, then every single time you're going to remove an input, you're going to have to retrain a new model to make sure that it's not learning this input. And then the accuracy drop is actually as a result of this removing of the informative feature, which is ridiculously expensive in the sense that every single time you want to do this experiment, you're going to have to retrain a model. And if you ever try to train something like on ImageNet, you know that if you have to train the model a couple of times, that's really expensive. Okay, so another paper which was particularly interesting kind of proposed these sanity checks. So before I go into the sanity checks, I wanted to take any questions up till this point here. Okay, so let's look at the sanity checks. So this paper was done in by Google Brain a couple years back in Europe. Well, they proposed two sanity checks. So the first sanity check is called model parameterized randomization test, which is basically what we do is that we have this trained model and we get the interpretations, and then we take this trained model and we completely randomize the network, and we end up with this untrained network. And what this is testing is that if these new saliency from the untrained network are dramatically different from the old saliency, then basically what that means is that the saliency map depends on the model parameters. If they give us the same saliency map, then the saliency methods are insensitive to changing in the model parameters. And interestingly, what they found is that you can have, so here what they did is that we have this original explanations. This is the original image, and we have these different saliency methods. And if you look at, for example, guided backpropagation, you find this really, really good appealing image that looks like this bird, and you think maybe, well, if you just look at this, if I had to choose, I'm going to choose guided backpropagation as the one that gives me best interpretation. However, if I start taking layer by layer and I cascadedly randomize the layer weights, you can see that guided backpropagation basically does not show almost no change in the saliency when you randomize the network to up to more than half the layers. While on the other side, if you take a look at smooth grid, and you can see that it's very sensitive to changing the model parameters, and that's kind of what we want. We want to make sure that these saliency map actually depends on the model parameters themselves. So just looking at what's more visually appealing is might not be actually correct in that case. So then they proposed another test, which is called data randomization test, where we take the data and we randomly commute the labels. So we end up with this data set that is completely random. And then we want to say that we would expect that the saliency map from the two classes to be significantly different. And basically what they said that if it's not, then basically if it's not, then the saliency methods don't capture any relationship between the instance and the label itself in the original data. So these were really cool and easy to do kind of sanity checks to make sure that your method is actually doing what you think it's doing. So this is so finally we looked into using synthetic data for evaluation, but let me take questions before I go into that. Okay, due to context, the model may still work well even if interpretability is not good in the previous method. So I'm not sure what you mean by that. So if you can explain what you mean by that or unmute yourself, you can help me understand what, yeah.
Yeah, what I was trying to say is that the background sometimes, like what if our saliency map is not good, the interpretability is not good, but due to that, what happens is that like our model still works well because it can take the context around and maybe make the predictions, or like
I mean, you're talking in this case of accuracy drop?
yeah, I mean like there may be cases where the opposites happen, that
Okay,
the
what?
accuracy doesn't drop, uh, like they are not directly proportional. I mean, inversely.
Yes, they're inversely proportional. So by removing so if you remove the features that the models that the saliency map says that are important, and then the accuracy improves, then basically these features aren't important. So basically the feature can be important for two reasons. They can be positively important. So for example, you would have a positive gradient, which means that these features were important to identify this dog as a dog, and then there were features that are negatively important, that the features that were like would have made this model make a wrong mistake, say identify this dog to a cat. And if you remove these features which help make that decision either positive or negative, well, you kind of, and these features are actually the features that the model used, you would kind of expect some sort of accuracy drop. Maybe not a dramatic accuracy drop, because you didn't remove all the features and you don't know exactly what the model is using, but you would expect some sort of significantly accuracy drop. But again, here there is this huge problem where you kind of don't know where this accuracy drop came for. Did it come for the removal of the features, or did it come for this just masking? Could you elaborate on the sanity checks for changing the labels? I wonder if self and semi-supervised method use a very few labels like SimClear would have better interpretability results. So basically, what the sanity check is doing is it's kind of wanted to test that if this interpretations are insensitive to label permutation, then basically what it doesn't tell me anything about the relationship between the inputs and the label themselves in the original data. So if I can do if I can change the labels to be anything. So if, for example, if I change the label to be from a cat to a dog, I'm going to get the same features that are important. If I change it from a cat to a car, I'm going to get the same features that are important, which means that it kind of does not capture any relationship between the input and the label itself. And in that case, if you want to debug the network and say why it's making the correct predictions, and if the goal of this interpretation is debugging, then in this case it wouldn't really make sense. If it failed this randomization test, then it wouldn't make sense to use these interpretations to debug the network. So yeah.
So yeah, thanks, Aya, for that explanation. So I guess I was really kind of misunderstanding here, as I was thinking that you would want to retain the same sort of salient features regardless of the label. But I guess that's not what we want here. And I don't know. I guess that's kind of interesting. Like, how do we reconcile what we're looking for in a good saliency map versus what we look for when we are trying to build good representations, for example? Because in some ways, it seems like we would want to capture the same concept of like pertinent features, but it seems like for saliency maps, we really only care about how it affects our final output. Would you say that's a fair characterization?
So yes, that's a fair characterization. And again, it depends on why you need to do this interpretation. For example, if you're doing it for debugging, then maybe that's kind of what you want to do, is kind of you want to see why the method did something wrong. But if you're doing this for another application, maybe you wouldn't really care about this data randomization test. One interesting thing is that you said, well, how would these methods perform on data with very small, a few labels like SimClear? And my answer is I don't know, and this would be really interesting to look into. Not sure if anybody looked into that yet, but that would be really interesting to look into.
Yeah, cool. I mean, the intuition is that it wouldn't help or that, it would fail a randomization test since it doesn't have the labels. But yeah, no, definitely interesting. Thanks.
Yeah, I guess so too, but it would be it would be interesting if that wasn't the case, but I'm guessing it would. Okay, so final evaluation of interpretation is synthetic data. So this work we did in our lab, and it's going to be published in this year's NeurIPS. Well, we decided to look into a different data set altogether, and the reason we decided to do that is that we know most of these methods are already evaluated on images and language. So, and there's very, very few or almost none evaluated on time series. And basically time series have these properties that are not, that you don't require the saliency method to be able to do in images and language, which basically be able to detect how feature important changes over time. So for example, you kind of have this concept of time in language, but the entire embedding represents a single feature. But in a time series, you would want to know every single feature has a different meaning. So you would want to know how individual features changes over time. So we decided to kind of create a synthetic data set and test how this how different methods perform for time series. So to create this data set, well, what we did is that we generated features, and we generated data sets where we have this time series, and then for every feature, we decided if that feature is informative at a particular time or not by adding or subtracting a constant mu. So here, for example, if you look at this, so this is like basically Gauss, this is noise, and then we have this, we define these box, the red box has informative feature by like adding mu or subtracting mu. And then we did this for different time series, like for example, for autoregressive series and for Narima and so on and so forth. And now we had this huge number of data sets. So we decided to say, to build a benchmark for time series interpretability. So we looked into different architectures. We considered the three main categories of architectures: recurrent networks, convolutional networks, and transformers. And we could consider different subcategories like LSTM and LSTM with input cell attention that I mentioned earlier. And then we looked at different saliency methods, which are both gradient-based and perturbation-based methods. And then we had many, many temporal data sets that I explained in the previous slides. And then we said, we thought about a little bit about the performance metrics, and we thought, well, we're going to look at the accuracy drop. But here in this case, since we know the distribution, when we're going to remove the feature, we're not just going to mask it with noise. There's just zeroed out. We're going to mask it with the original distribution, so we don't have to do this retraining that we did over and over again. And also, we're going to look at this weighted precision and weighted recall to make sure that these informative features, what are the precision and recall of the salient features with respect to the informative features. In that case, so for example, if I'm using a network for scientific discovery, I would want it to use all informative features. If I want to understand what features are actually informative, so that's why kind of precision and recall made sense for us. So what we found is quite interesting. First, we found that it does dramatically worse when you apply these methods to time series in comparison to what we had when we applied this to images, or what we had when we applied this to language. And so you can see here that, so these are not actually images, these are embeddings that are features in time. So you can kind of think about this as like time step 1, and these are feature embedding time step 2, and so on and so forth. And here in this, instead of considering it as an image, we kind of considered it as pixel image, where we basically, it's just a time series of embedding. And you end up with the saliency method that if you initially look at it, you kind of figure that it's completely garbage and useless and tells me nothing about what's happening or about informative feature whatsoever. And if you look at the precision and recall, you also get really, really bad precision and recall and really small accuracy drop. But if you take a closer look at this, you kind of see this trend where if this is the informative features, we're able to identify informative times, but in that particular time, what we identify as informative is all the features, regardless of what's actually informative. So here, for example, you can see that the small box kind of drags along from the beginning of the time step to the end of the time step. So basically, identifying all the features are informative. So why this happens is basically an open question. We do not know why this happens at all. But what we notice is that we can kind of improve the saliency method using this trick we call temporal saliency rescaling. So basically, the main idea is that if we are able to calculate to understand time contribution, so we're able to identify which time step was important, well, we're going to look at the time steps that are important, and then we're going to look at every individual feature within that time step. And then we're going to say that the feature contribution at the end is the contribution of the feature itself multiplied by the contribution of the time step itself. So one problem with this is that it's very, very expensive. So this is kind of like a workaround to improve these saliency methods in time series data, but this is not the solution. And what we kind of need to do is try to figure out why this is happening. And maybe this is the reason saliency methods don't necessarily fail in language when we have the entire embedding represents a single word, so the entire time represents one word, so we don't really care. We didn't look about how individual features matter. But when you look in time series where you care about individual features, it totally it fails. So when we did this temporal saliency rescaling, we got these kind of better saliency maps, and we got higher precision, weighted recall, and accuracy drop. And in this, you can see that it kind of identify important features. Again, this is kind of not a solution, it's just more of a workaround to improve the performance of saliency methods and time series. Okay, so far what I said is like a very high level overview of interpretability. There is so much more work in this area, and if you're interested in that, there's this book called Interpretable Machine Learning, which is online. It's pretty cool and really simple to understand. There's this framework called CAPTM in PyTorch, where it has all of these methods that we discussed, and basically you can just plug in the methods and just has really cool visualization that you can look into. And there's always like tutorials and workshops and all the main conference that explain about interpretability. So if you're interested in this area, you can always find these online resources. So that's all what I have today. If you guys have any questions about anything I said or interpretability in general, you can unmute yourself or write in the chat. The TSR results look really good. I think I understand how you get the important features. Could you remind me of how you get the important features? Oh, so here what we looked into is that if we remove this feature, how is the gradient going to change? And that's how we kind of calculated the contribution of the feature itself, the changes in the gradient when we remove this feature. Did you just sum up over time? No. So we kind of had to look into the contribution of removing the features themselves and seeing how that was the feature contribution. And that's why it's kind of expensive. Oh, it's expensive in general. Other questions? Okay.
If there aren't any more questions, let's join me and thank Aya for this great presentation. Thank you, Aya. Great talk. Are there any last-minute questions? So I'll add just one note. About the sensitivity of the interpretation to adversarial examples. As Aya mentioned, you can come up with adversarial perturbations that can keep the label as before, correct label, but it can drastically change the saliency maps. And if you do regular adversarial training, it doesn't necessarily decrease the quality of the saliency, saliencies itself on the clean examples, but it doesn't improve the robustness of the interpretations. That's what we have shown in the paper. But if you do adversarial training for the interpretation, that drastically improves the robustness of interpretation and saliency maps.